Hello, my dear viewers. Today, I'm introducing to you an important topic, an important project, which is about some intelligent IoT with ring beat acoustics for real-time, eye-safe laser control and malaria vector. So this project was conducted by my group, which is SWAI 5, and my name is Nachimuli Stella. As I proceed, these are the important fields I'm going to go through, which include the related works, the problem statement, the research questions and objectives, research contributions, methodology, database description, results, conclusion, and then others. To move on, here is a background or introduction to this project. So it has a goal, which is mainly to detect, track, and neutralize malaria vectors. This will be done through our very intelligent system, which will use the Internet of Things to detect and be able to know the actual position of the mosquito, malaria-causing vector, which is a female Anopheles mosquito. So moving on, here are some related works. So here we compiled some papers that talk about this project and specify some models and architectural limitations, plus some results that were got after the research was made on these models here. So there is the first paper, which is the risible PI13 for malaria neutralization, which included a CNN model, had some architectural limitations like short ranges, cameras only detection suffers from low light. So there was a problem of low light. So, and then on these results, we have the model worked on tracking demo and more prototypes. So that's one paper. We had another one, which is mosquito wing beat analysis and classification with deep learning. So that's another paper, which used 2D CNN, and then some architectural limitations, which included optical sensors needed very careful alignment. So there was crucial need of aligning the optical sensors to get accurate results. There is also its results. So moving on, I have some other papers, the convolutional neural networks related, real-time mosquito classification. These are also papers, Sandberg database, large scale acoustic mosquito database. And then we also have the other one, the last one. And then moving forward with my problem statements, which include the domain application problems and the computational problems. So these ones majorly talk about my project, showing us the the roles or the contributions of these projects. So here we're having that the primary domain application is the uncontrolled spread of malaria. As we all know, malaria is currently one of the biggest problems we are suffering as Ugandans. So there is need to solve this problem by the methods that have been used are so traditional that they can't suppress this problem. So we come up with this smart, intelligent IoT method to combat this problem, to solve it. And then on the computational problems, we see the steps we went through to solve this problem. Moving forward with some research questions and objectives. So major objective is to detect this vector. After we are going to detect it through geolocation or geotracking. And then the goal is to neutralize this vector and to enable scalable rural deployment. That's our goals. Moving on to the contributions. So mainly, we trained 3 different models, and finally, one with the accuracy that was best, and it was chosen. So some outputs, we got some heat maps of the malaria vector activity, we got some laser self-actuation. This is our system methodology. Here on the left, we have a flow diagram showing the processes we go through, like the acoustic sensing unit, we have sense the movement of the mosquito, and then we go to the IoT sensors that combine to give us a result, and then edge self processing, whereby we detect the mosquito, there is swarm fusion, whereby we collect all the information from the different IoTs to track, to get the 3D tracking of the actual position of the mosquito. And then the safety check, whereby we check that there is no human being in the surrounding. And then the laser actuation output, so we trigger the laser. Moving forward, this is a model architecture and mathematical foundations. This is one of the models we trained, the micro SCDNet model. And on the right is our mathematical computations and mathematical explanations of the model, what we go through to train this model or to get this model done. So that's it with that model. This is still the mathematical operations on the SCDNet model. We move forward to, this is another model. It's mathematical computation on the left, and then the architecture, whereby you go through the audio input, you go through the feature extraction, standard scalar. These are steps we go through to train this model so that it can detect our mosquito. There we have the input layer, and then the hidden layer 1, hidden layer 2. These are all steps, the output layer, and then the prediction. Still, the mathematical computations. This is the third model we trained, which is the GATT model, the graph attention networks. Yeah, so here on our left you have its architecture, some brief explanation on this model, moving forward to its mathematical foundations. So these are the databases we used the Hamburg database, which had 4 folders in it, which included .wav files and also included audio input databases, which aided our research and implementation. So on our right, you can see the EDA results and graphs. So here we have some species distribution, we have the species, the anopheles, the tulips, among others. We have some spectrogram here. We also have a waveform. These are all results obtained from our EDA training, EDA implementation and the data, and then some gender distributions, and then some missing values, how they were corrected. These are the results. Okay, moving on. This is a confusion matrix which shows the predicted classes. Mainly, we are focusing on the female Anopheles mosquito. So this is our confusion matrix. Some output results of the FNN, and then the micro SCD. So we got these are our results that show the loss, the accuracy, and then the validation. Yeah, those are our results. Moving forward, some output results. Here we are looking at the F1 score, whereby our precision is calculated by the whole. So basically, here we are looking at precision. Here we have some results on the spectrogram attention. Yeah, moving forward, there are some results of our models we trained, which is the micro SCD model, and then the forward neural networks, whereby our validations and the testings, the trainings, we show our results right there. Yeah, so the model selection, we basically chose to deploy the SCD model. Yeah, we had the best results. Deployment, then the demonstration of the deployed product. We deployed our smart IoT product to detect Anopheles mosquitoes. Basically, that's it for the product. Here we have some limitations. There was limited knowledge of tools like Kaggle. Yeah, basically that's it. Some future works. We shall be improving on our model. Moving forward, we would like to acknowledge the crucial people who helped us in this project. Our lecturer, Mr. Galuango Marvin, we acknowledge you. So, my dear viewers, thank you for viewing. Thank you for all your likes.